Before M-theory, strings seemed to operate in a world with 10 dimensions. These included one dimension of time, the 3 familiar space dimensions, as well as 6 extra dimensions, curled up so tiny that they're completely invisible.
Well, we think these extra dimensions exist because they come out of the equations of string theory. Strings need to move in more than 3 dimensions. And that was a shock to everybody, but then we learned to live with it.
But M-theory would go even further, demanding yet another spatial dimension, bringing the grand total to 11 dimensions.
We know that there would have to be 11 dimensions for this theory to make sense. So there must be 11 dimensions. We only see 3 plus 1 of them. How is that possible?
For most of us, it's virtually impossible to picture the extra higher dimensions. I can't. And it's not surprising. Our brains evolved sensing just the 3 spatial dimensions of everyday experience. So, how can we get a feel for them? One way is to go to the movies. We're all familiar with the real world having 3 spatial dimensions. That is, anywhere I go, I can move left, right, back, forth, or up, down. But in the movies, things are a bit different. Even though the characters on a movie screen look 3-dimensional, they actually are stuck in just 2 dimensions. There is no back, forth on a movie screen. That's just an optical illusion. To really move in the back-forth dimension, I'd have to step out of the screen. And sometimes, moving into a higher dimension can be a useful thing to do. So, dimensions all have to do with the independent directions in which you can move. They're sometimes called degrees of freedom. The more dimensions or degrees of freedom you have, the more you can do. That's right. And if there really are 11 dimensions, then strings can do a lot more too.
People found fairly soon that there were objects that lived in these theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be 3-dimensional, or even more. And with enough energy, a brain could grow to an enormous size, perhaps even as large as a universe. This was a revolution in string theory.
String theory has gotten much more baroque. I mean, now there are not only strings, there are membranes. People go on calling it string theory, but the string theorists are not sure it really is a theory of strings anymore.
The existence of giant membranes and extra dimensions would open up a startling new possibility. That our whole universe is living on a membrane inside a much larger, higher dimensional space. It's almost as if we were living inside a loaf of bread. Our universe might be like a slice of bread, just one slice in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes that are right next to ours, in effect, parallel universes. Not only would our universe be nothing special, but we could have a lot of neighbors. Some of them could resemble our universe. They might have matter and planets and, who knows, maybe even beings of a sort. Others could certainly be a lot stranger. They might be ruled by completely different laws of physics. Now, all of these other universes would exist within the extra dimensions of M-theory, dimensions that are all around us. Some even say they might be right next to us, less than a millimeter away. But if that's true, why can't I see them or touch them?
If you have a brain living in a higher dimensional space and your particles, your atoms, cannot get off the brain, it's like trying to reach out, but you can't touch anything. It might as well be on the other end of the universe.
And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe.
It is a powerful idea, especially because it may help solve one of the great mysteries of modern science. It has to do with gravity. It's been more than 300 years since Isaac Newton came up with the universal law of gravity, inspired, as the story goes, by seeing an apple fall from a tree. Today it seems obvious that gravity is a powerful force.
It would seem to most people that gravity is a very important force. It's very strong. It's very hard to get up in the morning, stand up. And when things fall, they break because gravity is strong. The fact of the matter is that it's not strong. It's really a very weak force.
Gravity pulls us down to the Earth and keeps our Earth in orbit around the sun. But in fact, we overcome the force of gravity all the time. It's not that hard. Even with the gravity of the entire Earth pulling this apple downward, the muscles in my arm can easily overcome it. And it's not just our muscles that put gravity to shame. Magnets can do it too, no sweat. Magnets carry a different force, the electromagnetic force. That's the same force behind light and electricity.
It turns out that electromagnetism is much, much stronger than gravity. Gravity, in comparison, is amazingly weak. How weak?
The electromagnetic force is some 1,000 billion times stronger. That's a 1 with 39 zeros following it.
The weakness of gravity has confounded scientists for decades. But now, with the radical world of string theory, filled with membranes and extra dimensions, there's a whole new way to look at the problem.
One way of approaching the question of why gravity is so weak compared to all the other forces is to turn the question completely on its head and say, no, actually, gravity isn't very weak compared to all the other forces. It just appears to be weak.
It may be that gravity is actually just as strong as electromagnetism, but for some reason, we can't feel its strength.
Consider a pool table, a very large pool table. Think of the surface of the pool table as representing our three-dimensional universe, although it is just two-dimensional. And think of the billiard balls as representing atoms and other particles that the universe is made out of.
So here's the wild idea. The atoms and particles that make up stuff in the world around us will stay on our particular membrane, our slice of the universe, just as the billiard balls will stay on the surface of the pool table.
Unless you're a really bad pool player.
But whenever the balls collide, there is something that always seeps off the table. Sound waves. That's why I can hear the collision. Now,
Now, the idea is that gravity might be like the sound waves. It might not be confined to our membrane. It might be able to seep off our part of the universe. Or think about it another way. Instead of pool tables, let's go back to bread. Imagine that our universe is like this slice of toast, and that you and me and all of matter, light itself, everything we see, is like jelly. Now, jelly can move freely on the surface of the toast, but otherwise it's stuck. It can't leave the surface itself. But what if gravity were different? What if gravity were more like cinnamon and sugar? Now, this stuff isn't sticky at all, so it easily slides right off the surface. But why would gravity be so different from everything else that we know of in the universe? Well, it turns out that string theory, or M theory, provides an answer. It all has to do with shape. For years, we concentrated on strings that were closed loops, like rubber bands. But after M theory, we turned our attention to other kinds. Now we think that everything we see around us, like matter and light, is made of open-ended strings. And the ends of each string are tied down to our three-dimensional membrane. But closed loops of string do exist. And one kind is responsible for gravity. It's called a graviton.